The next named reaction we're going to be learning about is Friedel Crafts reaction. So these are actually a set of reactions which were developed by two scientists, Charles Friedel and James Kraft, in the year 1877. So the main aim of this particular reaction was to add various substituents to the benzene ring, and its uses are versatile, so that's why it comes up in various chapters. First, we look at it from the perspective of reaction of haloarenes. So it's a substitution reaction, and it's an electrophilic substitution reaction. So what happens is, here we will be taking a haloarene, and this reacts with alkyl or acyl chloride in the presence of anhydrous AlCl3, which acts as a catalyst, to give us para-substituted or ortho or para-substituted alkyl / or rather acyl benzene haloarenes. First of all, chlorine. Let's take chlorine for example, chlorobenzene. So this is the haloarene. So chlorine actually is supposed to be electron withdrawing in nature. So it has to ensure that this meta position is what will get activated. But what happens is, it also possesses a lone pair of electrons, and that is why, so it shows both a -I effect as well as resonance effect. Okay, since it shows both these effects and resonance effect takes precedence, halogens are actually orthopara directing, but they are a ring deactivating group. So that is why all the electrophilic substitution reactions for haloarenes that you would have learned that ortho and para substituted products are the ones which are formed. So in this case, so let's take chlorobenzene. Okay, so chlorobenzene is going to undergo two reactions. One will be acylation, the other will be alkylation. So let's start with alkylation. So here you have chlorine. It reacts with methyl or chloromethane and anhydrous AlCl3 as a catalyst. This leads to the formation of two products. Okay, one will be in the ortho position and one will be in the para position. So if you would like to pause and think about which of these products is going to be major and why that is the case. So first of all, chlorine in itself is actually a big atom. Okay, this looks like a balloon for some reason. Okay, it's chlorine. It's a big atom as such. And then you have carbon, which is attached to 3 other hydrogen atoms. So obviously there will be some amount of steric repulsions between the chlorine atom and the methyl group, and this is why the ortho product is the minor product, whereas the para product will be the major product. So the ortho product is the minor, para product is the major product, and so we'll just write that here. So this is minor, this is major. Now the name of these compounds would be 1-chloro, 2-methyl, 2-methyl benzene, whereas this is 1-chloro, 4-methyl benzene. Now the same chlorobenzene can also undergo acylation reaction. So when it undergoes acylation, CH3COCl in the presence of anhydrous AlCl3, okay, as a catalyst to form. Again, here also we'll have two products, that is ortho and para. And it's even more obvious in this case that the ortho product will have a steric hindrance, and because of that our ortho product is going to be the minor product. So this will be minor, whereas this product will be major. Okay, so basically this chlorine is getting removed and you're getting two products, that is at the ortho and the para position. So the minor product is called as 2-chloroacetophenone, whereas this product is called 4-chloroacetophenone. So that is about reaction of haloarenes. First of all, you have a chlorine, a halogen group. Generally chlorine, bromine, all of these are technically supposed to be meta-directing in nature, but because of their two effects, they also show inductive effect as well as resonance effect. Because of that, they direct the incoming electrophile to the ortho and the para position. And the reason the para product is considered the major product is because in this case you have an amount of steric hindrance taking place, whereas in this case there is no steric hindrance, and because of that our para product is the major product. In case you are not clear about this, suppose you have a substituent X, 1, 2 and 3. 1 is ortho, 2 is meta and 3 is para, just in case. So that is about reaction of haloarenes. The next one we'll be learning about with respect to Friedel Crafts reaction is reaction of anisole. Let me just erase this a little quickly. So even in reaction of anisole, it follows the same rules. Okay, here also we'll be reacting it with an alkyl or an acyl chloride with anhydrous AlCl3 as the catalyst. So it's the same thing happening here as well. So reaction of anisole. Okay, so basically anisole will react with alkyl or acyl chloride in the presence of anhydrous AlCl3 as the catalyst. Okay, and you will get alkyl or acyl substituted anisole. So here anisole, the same thing. If you notice, it's the same thing happening. Only thing, in case of haloarenes we had alkyl or acyl haloarene. Here we have alkyl or acyl substituted anisole. It's the same thing. So let's look at the reactions. First of all, anisole is a benzene ring having an OCH3 group. And this reaction is then alcohols, phenols and ethers, and this is then ether. It has an oxygen between two carbon atoms. So here we are reacting it with, again we are going to be using methyl chloride, okay, or chloromethane in the presence of anhydrous AlCl3 as a catalyst. Now OCH3 is obviously ortho-para directing in nature, and so you get two products. Based on whatever we studied in the previous for the previous reaction, which of these products do you think is going to be the major one? If you guessed para, you are right. This is because para also, again in this case as well, will have no steric hindrance, whereas this will have steric hindrance between OCH3 and the methyl group. So this becomes the minor product, whereas this becomes the major product, and this is called 2-methoxytoluene. We're changing the name itself, like we went from anisole to 2-methoxy. This becomes the substituent, this becomes our main ring, parent ring. So 2-methoxytoluene or 4-methoxytoluene. And 4-methoxytoluene is the major product because of the fact that these do not have any steric forces in between them. The next one is obviously anisole on reaction with acyl chloride. You can write the product on your own at this point. One more thing, do not learn these reactions, these set of reactions separately. You're just confusing yourself in the process. If you do it all together, then all of them follow the same set of rules and regulations, right? So it's just easier. So here also you get two products. One is going to be ortho-substituted, and one is going to be, yes, para-substituted. And obviously the para-substituted product is the major product. So this is called as 2-methoxy acetophenone. That's the minor product. Whereas this one is called 4-methoxy acetophenone. Oh, it's not visible. Yeah, major product. So yeah, so anisole reacts with alkyl or acyl chlorides to give us two products. And to give us two products, one will be the ortho, one will be the para position. So if the para position is major because of less steric hindrance, or no steric hindrance rather. And the next one we'll be learning about is synthesis of ketones. So ketones are also synthesized using this method, and specifically ketones only. And if you think about it, why do you think we can use this for the synthesis of ketones? So synthesis of ketones, excuse me, benzene reacts with acyl chloride in the presence of anhydrous AlCl3 as its catalyst to give us an acyl benzene. And what is an acyl group? Acyl is COCl and R. So RCO, this part gets substituted on the benzene ring, and that automatically becomes a ketone, and that's why we're using this for the synthesis of ketone. So let's look at the reaction. Benzene reacts with acyl chloride. So let's take CH3, or instead of actually writing CH3, it can be anything, right? So AR, that is, it could be an aryl, or RCOCl. Okay. I'm sorry, this shouldn't have been acyl benzene, that should have been ketone. It should be ketone. Okay, so it reacts with anhydrous AlCl3 to give us CO. It could be an R group or an aromatic group. So all of these reactions, all of these are Friedel Crafts reactions. If an alkyl chloride is used, it's called an alkylation. When an acyl chloride is used, it's called an acylation reaction. Now, aniline, benzoic acid, all of these compounds do not undergo Friedel Crafts reaction. Actually, even phenols do undergo Friedel Crafts reaction, but I believe that's not given in your textbook. So that's about Friedel Crafts reaction. So Friedel Crafts reaction follows the basic thing that benzene and substituted benzene compounds react with alkyl or acyl chloride in the presence of anhydrous aluminium chloride to give rise to various products. And that's all about Friedel Crafts reaction. Do not learn all of these reactions separately and basically find it very confusing. Honestly, when I was in grade 12, I found Friedel Crafts quite confusing because I actually, without realizing it at that time, I actually learned all of these as separate reactions. And because I did that, I actually got confused between all of them at one point. So it's easier to just learn it in this manner. And basically, benzene or substituted benzene reacts with alkyl or acyl chloride in the presence of anhydrous AlCl3. Remember, if anhydrous AlCl3 as a catalyst, it's Friedel Crafts reaction. So with that, we're done with this particular named reaction. In the next one, we'll be learning about Lucas test. Do check it out.